A paper just came out today that honestly might completely change how we think about a whole corner of the mathematical universe. This is a story about finding one single, perfect, simple rule that's been hiding inside some of the most chaotic things you can possibly imagine. So let me ask you this. How do you find order in chaos? And I don't mean just a messy room. I mean true, infinite, mathematical chaos. It's kind of like trying to listen to a symphony of pure random noise and picking out the one single note that somehow governs the whole thing. Well, that's the absolutely massive challenge this paper decided to take on. So our story begins in a world you might think you know, fractals. But I want you to forget all those beautiful, spiraling posters you might have seen. We are going somewhere much, much wilder. Okay, so on the left, you've got the fractals we're all used to seeing, right? They're super intricate, sure, but at the end of the day, they're predictable. On the right? Whoa, that is the wild frontier. These are called non-holomorphic fractals, which is really just a fancy way of saying they don't play by any of the usual rules. They are jagged, they're chaotic, and their behavior can just change in an instant with no warning. And deep inside this wild frontier lies a very specific mystery, and it all revolves around one number, called the Stokes constant. So scientists had a piece of the puzzle. They had this formula, which they knew described how these weird fractals were behaving. But there was this huge question mark smack dab in the middle of it, this exponent, beta. They knew a number was supposed to go there, but nobody on Earth knew what that number was. It was the one missing key to the whole thing. So what is this Stokes constant anyway? Well, the slide calls it a mathematical fault line, and that is the perfect way to think about it. Imagine you're walking across a landscape where the laws of physics are totally consistent, and then you cross this invisible line and suddenly, boom, gravity works differently. The Stokes constant is the number that actually measures the power of that sudden, shocking change. But look, if it's just a number, why was it so incredibly hard to find? I mean, this was not some simple calculation. For years, mathematicians had thrown their absolute best tools at this problem, and every single one of them had failed. Well, the problem was that all the standard mathematical tools were completely useless here. The paper uses this great phrase, degenerate by construction, which basically means the problem itself was perfectly designed to break all the old methods. It was like trying to open a lock with a key that was specifically engineered not to fit. They needed a brand new key. And that new key? It wasn't found in numbers. It was found in shapes. The huge breakthrough came when the researcher Michael Bird stopped trying to just calculate the answer and started to look at the problem's geometry instead. The answer wasn't hiding in an equation. It was hiding in a landscape. The groundbreaking idea here was to translate all that complex math into a physical shape, a terrain with mountains and valleys and ridges. And this new method is called half-thimble geometry. It's so clever. Here's how it works. First, you map out that mathematical landscape. Then you find the most important points, like the highest peaks and the lowest valleys. Now, this is the brilliant part. You trace a very specific path across this terrain. By just watching how that path is forced to interact with one of those fault lines we talked about, the answer just reveals itself. The geometry of the landscape leaves only one possible solution. And this new geometric method, it didn't just give an approximation or a close enough. No, it gave a perfect, simple, and absolutely stunningly precise answer. So after all that, after exploring this infinitely complex, jagged, unpredictable mathematical world, what was this fundamental number, this exponent beta that had been hiding all along? 1/3. That's it, just 1/3. A simple, elegant fraction was the secret rule that was governing all of that chaos. And this wasn't some lucky guess. Not at all. As the paper says right here, the answer is exact. The geometry of the problem, the shape of that mathematical landscape, it literally forced the answer to be 1/3. It was the only number in the universe that could possibly work. Okay, so why does one little number matter so much? Why is it such a big deal? Because finding it wasn't just about solving a single tricky math problem. What this discovery really represents is a second universal law for this entire family of non-holomorphic fractals. It's like finding a new law of physics, but for this very specific, very strange mathematical universe. It's a fundamental rule that applies everywhere inside it. So let's just step back for a second and appreciate what was just accomplished here. In one single paper, the author proved a new universal law, discovered the exact number that governs it using a brand new method, explained precisely why every other attempt in history had failed, and then handed over the complete computer code so anyone on Earth could check the work. I mean, that is a grand slam. But of course, finding one key just makes you wonder about all the other locked doors. In science, every answer just opens up a whole new set of fascinating questions. You see, the paper solved for beta, that 1/3, but the original formula has another mystery variable in it, C. The author himself calls finding its value the natural open problem. And it just makes you wonder, right? If a simple, perfect fraction like 1/3 was hiding in all of that infinite chaos, what other beautiful universal laws are still out there, hiding in plain sight, just waiting for someone to come along and look at the problem from a totally new angle?